Now, when you talk about energy possessed by a mass inside a gravitational field, you know that energy as gravitational potential energy. In this chapter, normally is given the symbol U. Okay. Now in AS, we normally define gravitational potential energy is the energy stored in a body due to its position inside a gravitational field, or rather is the energy stored inside a mass due to its position inside a gravitational field. So this one was correct at AS level. Okay, if we ask you what's the definition of gravitational potential energy, and then you say this one is okay for AS. But then if we ask you the same for A2, you cannot use that. You use back the same definition. You have to use a more precise definition, which is actually the work done in bringing a mass from infinity to a point in the gravitational field. Okay, so if we ask you in A2, what is definition of gravitational potential energy? It is work done to bring a mass from infinity to a point in the gravitational field. Okay, so why do we say this? In your AS and work energy power last time, we said that work done on an object is used to increase its energy in some form. Okay, in some form, it can be gravitational energy, gravitational potential energy, electric potential energy, elastic potential energy, or any kind of other energies. Okay, in general, last time in AS physics, we normally told you that whatever work that you do on something normally is used to change the energy of the object. So here you can probably think of it as whatever work you do on an object is used to increase the energy in some form. Let's just say, for example, GPE. Okay, so the idea is this. If let's just say your GPE is 0 at one point, and let's just say at a random point A, and then after that you go and bring it to another point B, you bring it from A to B, it involves work done. Okay, if you were to bring it from A to B, it involves work done. So whatever work that you do would end up being the GPE at this point here. Okay, because the baseline is that you started off from 0 at some point where GPE is defined as 0. If you go and bring it to some other point inside a gravitational field and you do work, whatever work that you've done is actually the GPE at that point. That's why the definition is like this right now, where they say to you, work done in bringing a unit mass from infinity to a point in the gravitational field. Okay, the thing here is that when you are at infinity, your GPE is actually 0. Okay, now there's a common misconception that your GPE on the surface of the earth is actually 0. Okay, this is something that a lot of people tend to think. If I tell you that this is the surface of the earth, and then you have a person standing here, half the time people will always say that, oh, the GPE on the ground is 0. This is actually not correct. Okay, your GPE is actually not going to be 0 on the ground where you're standing at, because the idea here is that if a hole suddenly opens up beneath the person will actually still fall into the ground, right? Okay, so that person still falling into the ground implies that there's still changes in GPE. So GPE cannot be 0 here, okay, because you still can move down, so you still can have changes in GPE. So you can still have changes in GPE. This one cannot be considered as 0. All right. So you may also be thinking that, oh, the center of the earth is where GPE is 0. This is also not true. Okay. GPE is not 0 at the center of the earth also. Neither is it 0 on the surface of the planet or on the surface of the earth. Where GPE is 0 is actually at infinity. Okay, where you are talking about distances at infinity, your GPE is actually 0 there. Okay, Now, the reason why we say GPE is going to be 0 at infinity is because at infinity, there is no gravitational force, okay? So remember last time, when you're talking about work done is force times distance, right? So there needs to be a force to have work done in the first place, to have work done, okay? You need to have force in the first place to have work done, because the equation for work done is W equals to Fs, right? Or W equals to Fd in some textbook, okay? You need to have force in the first place to have work done. So here, if you recall that Fg is gml over r squared, what happens if r is at infinity? So if r is at infinity, this one is basically you dividing by infinity. Your Fg would actually be 0, isn't it? Okay, so at infinity, you actually have no gravitational force. So when you have no gravitational force, it also means that you have no capacity to do work. Therefore, GPE will be 0. This is where your GPE is 0. Okay, it's at infinity. Okay, so your GPE at infinity is 0. All right, so that one is your reference point, okay, at infinity. So if let's just say I tell you right now, this is planet Earth, and then this one is at infinity, and then I'm interested in the GPE value at some point here, by definition, the GPE at this point will be whatever work that I do to bring a mass from infinity to this point. Okay, so whatever work that I do to bring the mass from infinity to this point will be my GPE at this point itself. That's what this definition is trying to tell you. Okay, now when you're talking about GPE values at a particular point, GPE values at less than infinity will always be negative. Okay, there's a reason why we say that GPE values will always be negative. Okay, you can look at it in a number of ways, in two different directions actually. So what do I mean by that is this. Say for example, you have a mass at infinity right over here. This one is already established that GPE is going to be 0. Okay, and then this is the point that we are interested in, whose GPE value we're interested in. Now, if you bring a mass from infinity to this point, you can think of it as this. In the first place, if let's just say the mass at infinity here goes slightly out of position for infinity, you will start to have a gravitational force, isn't it? So the thing here is this. If you really have a gravitational force, if let's just say you just nudge the mass a little away from infinity, you're going to have a gravitational force acting on the mass, okay? So if you already have a gravitational force acting on the mass will actually move by itself from infinity to this point, because the gravitational force itself is actually pulling it from here to here. The thing here is that you do not need to purposely apply a force to push the mass from infinity to here. So in your current case, we will actually say that going from infinity to this point, going towards the left, work is done by the mass. Okay, the mass itself is doing the work. You are not doing work on the mass. Okay, so one way to know whether it's work done by mass, you can just think of it as no external force applied to move it. No external force. Yeah, I forgot to mention. You bring a small mass from infinity to this point. Okay, the big mass here remains as it is. It doesn't do anything. This mass, big mass, is the one producing your gravitational field. Okay, but I'm interested in the gravitational potential energy at this point inside the gravitational field produced by the big mass. Okay, so right now I go and use a test mass right now. The test mass is my small mass m. So I'm trying to bring the test mass from infinity to a point inside the gravitational field. So because by definition, we know that gravitational potential energy at a point is whatever work that you did to bring the mass from infinity to that point. If you bring a mass from infinity to this point, by right, there's already a gravitational force acting on the mass. You don't need to purposely apply any external force to bring the mass from infinity to this point. Okay, so no external force applied by anyone. Work is actually done by the mass. So when work is done by the mass, what we'll tell you is that GPE will decrease. Okay. If work is done on mass, GPE increases. But if work is done by mass, GPE decreases. Okay, so this one is what's happening right now. If you're going from infinity, work is done by the mass, GPE decreases from 0, because here is 0, right? So you go towards the left, GPE is decreasing in value. So obviously GPE will be negative in value. Okay. So if mass is brought from infinity to a point in gravitational field, work is done by the mass since gravitational force pulls the mass towards the other larger mass, thereby decreasing its GPE. And since GPE is 0 at infinity and GPE is decreasing, moving away from infinity, the resulting GPE value must be less than 0. In other words, GPE is decreasing from 0 lah. So your GPE must be negative in the first place. Okay, so if you think of it as that, GPE value must always be negative. Now, you can also think of it the other way around also. What if I don't bring a mass from infinity to that point? Instead, I did it the other way around, where I tell you I bring the mass from that point all the way to infinity. Would my value still be negative? You will actually get back that same conclusion. All right. Now, but in your current case now, it's a bit different. Slightly different. You need to modify it. If you're talking about at this point, you already definitely are going to have a existing gravitational force here, pulling the small mass, the test mass, towards the big mass. Okay. Now, if you wanted to bring this mass all the way to here, there's already an existing gravitational force trying to pull it in the opposite direction. If you had wanted to push this mass all the way to infinity, you would actually need to overcome this gravitational force in the first place. So in your case, you actually need to purposely apply an external force to overcome this gravitational force so that you can move the mass from this point all the way to infinity. Okay, so it's because of this that we will say that when you want to go from here to infinity, work is actually done on the mass. Okay, work is done on mass. Okay, so the work, when work is done on the mass, GPE increases. Okay, but in your case, it is increasing to GPE 0. It's increasing to 0. GPE increases to 0. So how can you have a value increasing to 0 in the first place? That's only possible if GPE value was negative in the first place. Therefore, GPE is negative also. Okay, right? You can explain it in two different directions. Either you bring the mass from infinity to that point, or you either bring the mass from that point to infinity. You will still get the same conclusion that GPE value is going to be negative. Okay, so when work is done on the mass, this one we say that external force is applied to overcome the gravitational force. Okay. So this is why I know this is work done on mass, because I had to purposely apply a force in order to move it. And when I purposely apply a force in order to move it, I'm actually doing work on the mass. So whatever work I do on the mass is increasing its GPE value. But it so happens that in your case, it's increasing to 0 right now. So GPE value must be negative. Okay. So this is what the other statement is actually saying. Conversely, if a mass was brought from a point in the gravitational field towards infinity, work is now done on the mass to overcome the gravitational attractive forces, thereby increasing its GPE. Again, since your GPE is at infinity is 0 and GPE is increasing towards infinity, your GPE value in the first place must be less than 0. In other words, negative. If it's less than 0, that means negative value. Okay. So GPE values at any point less than infinity will always be negative. That's why here we'll tell you, if you want to find GPE values at any point, you just use this equation, and that equation has a negative sign to it to tell you that GPE value is negative. Okay, so you want to find GPE values at a point, you will need to use equation U equals to negative GMM over R. Okay, the negative sign here is meant to tell you that GPE values is negative, like what I've just explained to you. Okay, so when you do calculations involving GPE, always make sure to put in the negative. The negative sign is actually pretty important. Okay, because gravitational potential energy is a scalar quantity. Okay, it does not have any direction, only value, only magnitude. If you have any negative sign, it is already an indication of your value, not direction. What I mean by that is this, maybe it's a bit confusing for you. If I tell you this now, I tell you for vectors, 5 Newton versus negative 5 Newton. Automatically, you will tell me that this one is actually acting in the opposite direction, right? Okay, so for the cases of vectors, negative sign is just simply telling you it's just acting in opposite direction. But what if I tell you for scalars? I tell you, say 15 degrees centigrade versus negative 15 degrees centigrade. You won't tell me that this negative is just saying that temperature is acting in opposite direction, right? This is actually just saying that it is actually this negative here, you won't associate it with direction. Instead, you associate it with value, or rather how hot something is, how hot something is, isn't it? So 15 degrees is considered maybe warm. Negative 15 degrees is considered to be very cold. Okay, so the negative here isn't telling you direction. It's actually telling you a measure of its value. Okay, so for scalars, like gravitational potential energy here, the negative sign is quite important. You need to put it in, all right? And this negative sign is actually not an indication of direction for a vector. It is an indication of value. Okay. Another thing that I should probably mention to you is this. Just now it was mentioned to you that the GPE value at a point is actually the work done to bring a test mass from infinity to this point, right? So sometimes people will say, okay, if that's the case, GPE is actually equal to work done. Can I just say that it is force times distance, where in my case, the F is my gravitational force, and then my S is basically my R, the distance moved from here. Okay, maybe I later not use R. My S is this one. Okay, from infinity to this point. Now the answer is you cannot do that. All right. Because some people will say, why is it that my GPE value, I need to specifically use GMM over R? Why can't I just use Fs, where I say that F is the gravitational force, S is your distance move from infinity to whatever point that is. Now, the thing here is this. Last time in AS, when you guys wanted to use work done as the product of force times distance, there was a condition to use this equation. That one being F must be constant. Okay, F must be constant in the first place for this equation to be valid. Now, in your current case, when you are bringing a mass from infinity all the way to your point that you're considering, notice that your R, the center to center distance between the masses, is actually varying. Gravitational force is GMM over R squared. So Fg is actually inversely proportional to R squared. So if you bring your mass from infinity to a point, whatever point that is, your R is actually not constant. Therefore, your Fg is also not going to be constant. Okay. So the fact that your force is not constant in the first place automatically would mean that you cannot use this equation. You cannot use this. That's why I wrote that in the notes somewhere in the next page. Work equals to force times distance cannot be used to derive the equation that you see, which is this one, because force is not constant here. Okay, we cannot use that. All right. The actual way that they got the negative GMM over R was actually through this. They actually use integration from infinity to distance R, where they say is GMM over R square dr. Okay, so there's a derivation for it. To get the GPE at a point, we know that it's work done to bring a mass from infinity to that point. So, but because the nature of the force was not constant, we cannot use W equals to Fs. Instead, we have to use integration, where we say we integrate the function of GMM over R square from infinity to R with respect to R. Then we will eventually get this. Okay. But this one, the derivation is not required in your syllabus now. You're not really required to know the derivation for GPE. All you just need to know is that if I'm interested in GPE at a point, the GPE is just negative GMM over R. Okay. If I'm interested to find the GPE values between 2 points, I will just take the difference in GPE between those GPE energy between those 2 points now. Okay. Where in my case, for example, let me just draw something here for you. If this is my big mass M, and then this is 0.1, and then this one, sorry, these are the 2 different points. This is say 0.1, and then this is say 0.2. I'm interested in the GPE values between these 2 points. What's the change in GPE between these 2 points? So at 0.2, the GPE value by right is negative GMM over R2. At 0.1, the GP is negative GMM over R1. If I want to take the difference in GP between the two values, this one will be U1 minus U2. Okay. Generally, take the higher value minus the lower value. Okay, but when you go and sub in your values to find the difference, don't omit out your negative. Okay, please make sure the negative sign is still there. Okay. So just something to take note of, right? I think I mentioned this also in AS physics. I'm not sure whether I mentioned for your class. To find changes in scalar, in scalar quantities such as energy always take higher value minus the lower value. Okay, so in my case, I'm taking changes in GP between 2 points. I would tend to take the higher value minus the lower value. U1 is actually higher value. Okay, wait, let me just write. Okay. This one, U1 will actually be higher value. U2 will actually be lower value. Okay. Now, because of this, you see, this one is say R2. This one is say R1. You can think of it as this now. Why is U2 going to be having a lower value GP? Because it's at lower height. This is the easier way I can mention to people. Because this one is at a lower height compared to this one, right? U1 is a higher value because it is at a larger height. Because this is something like what you guys learned last time in AS. If something is a smaller height, your GP is lower. If something is at a larger height, your GP is higher. Okay, so you can just think of it as that. Generally, the larger your height, the larger your GPE. Okay, so this one, maybe I better make my term more consistent, smaller height. Okay, right? So this is one thing to note. To find change in GPE, just use this. Okay, now you may be wondering also, last time in AS, we found change in GPE between 2 points by using equation mg delta h, right? Okay, now the mg delta h that time is only for small distances less than 1000 meter, where g remains constant. Okay, so we know that g is actually negative g, sorry, not negative, there's no gm here, there's no negative here, this gm over r square, right? Where we say that g is inversely proportional to r square. So in general, if your r changes a lot, your g will change a lot. Okay, so last time in AS, we tended to use this change in GP equals to mg delta h. That one was okay to use because the distances involved was just less than 1000 meter, where the field strength is still approximately constant. But when you're talking about the current chapter, where your distances involved is very, very large, all the way into outer space, which is definitely more than 1000 meter, your G is not constant anymore. Okay, it will continuously vary. So we cannot use this equation from AS. In AS, we can, because G is already can be assumed to be constant due to the small distances involved. But in A2, because of the distances involved being very, very large right now, G is no longer constant. We cannot use that old equation. Okay, so we had to use the previous one, this one. This one is actually the more accurate one. Okay. Okay, now there's also another different quantity called gravitational potential. Okay, previously you learned gravitational potential energy. Okay, the new term that you're seeing here is just the same thing, but without the energy. It's just called gravitational potential. Okay, now gravitational potential is kind of the same as gravitational potential energy, just that it's per unit mass. Okay, now when you see this little symbol, this is actually not theta. Okay, it is not the symbol theta. It's actually a Greek symbol called phi. Okay, theta is written like this. Phi is a circle with a line across it like this. This one was theta. This is phi. So gravitational potential is usually denoted by the symbol phi. Okay, so the definition for gravitational potential is that it's similar to gravitational potential energy, just that it's for per unit mass. So gravitational potential can be defined as work done in bringing a unit mass from infinity to a point in the gravitational field. So if you try to write it down in equation form, this means that this means that gravitational potential is gravitational potential energy divided by mass. Because you see, if you look at these two statements itself, work done in bringing mass from infinity to a point in the gravitational field, this one was already the definition of U, or rather GPE. If you suddenly add per unit mass, it means U divided by M. Okay, that's why it says GPE, but in terms of per unit mass. Okay, so phi is U over M, but at the same time, you know that U is negative GMM over R. So you sub inside the equation, you will notice that the small m will actually cancel each other off, giving you phi equals to negative gm over r. Okay, so for gravitational potential, you can actually have two different equations. Either phi is u over m or phi is negative gm over r. All right. So same thing like before, gravitational potential will always have negative sign to it because its value is always less than 0. Okay. Then the last thing I should probably mention to you is this. Now, in addition to finding change in gravitational potential energy between 2 points, we can use this equation. We can use, when we want to find change in gravitational potential energy, we can use this equation. There's also another simpler equation we can use, which is this one, where we say that change in GPE between 2 points is actually the mass times the change in potential. It actually came from this, where we say that this equation here, phi is u over m, right? Where we can say that if phi is u over m, u is m phi, but u was actually my GPE lah, okay? Now, GPE is m times potential. If I go and introduce the change symbol inside, I will get delta GPE equals to mass times delta phi. This is how this equation came about. It's actually from the definition at the top. Okay. GPA at a point is the mass times the potential at that point. But at the same time, I can actually modify this equation to give me change in GPA between 2 points is actually the mass times the change in potential between the same 2 points. Okay. So this is gravitational potential. Okay, now there is one last thing, escape velocity. Let me just go through this and then we're done with the chapter already. And after that, we can start doing some of the questions. Okay, now, so last thing that you will need to learn is something called escape speed. Okay, escape speed is pretty straightforward. Now, when we want to launch a satellite from a planet, let's just say, for example, this is our planet here. We want to launch some object far off into outer space. It could be a satellite, it could be a rocket, it could be anything. The thing is that generally when we want to launch an object out into outer space so that it never returns, the object must be launched with a certain minimum speed called escape speed. Okay, so if that object is launched with a speed less than this escape speed, it will never be able to escape from the gravitational field of the planet that it is on. Okay, you always need to have a certain minimum speed called your escape speed in order to be able to escape all the way into outer space. If you don't have that, gravity will just pull your object back towards the planet itself. Okay, so what you're interested to find out is what is this escape speed, VE here. Okay, so when you want to derive the escape speed, there's actually just a simple conservation of energy principle that you need to apply. You consider two different spots. let's just say a spot on the surface of the planet that you're launching it from, and at infinity, which is the place that you've already escaped to and not returned. Now, it was really mentioned to you before at infinity, your GPE value would be 0. Okay. And then on the surface of the planet that you're launching from, your GPE ought to be negative GMM over R. All right. Now, what about the KE then? If you're talking about the KE, on the surface of the planet that you're launching from, the KE will be half mve squared, where VE is your escape speed. But at infinity, your KE ought to be 0. Okay, now why do I say that the KE would be 0 here? It is due to this fact. You see, when you launch anything, say for example, say you launch a rocket or a satellite, okay, and it moves all the way to infinity. Let's just say that this one is here is infinity. Okay, your direction of motion is here. Okay, this is your direction of motion, but you are still under the influence of your gravitational field. You're still being pulled by gravity, where gravity is pulling you in this direction. Okay, so if you consider this, your motion is towards the right, but your gravitational field is towards the left. Your gravitational force towards the left is in the opposite direction. What this would mean to you is that you would actually start to slow down, okay? As you move towards infinity, you will actually start to slow down. So it will be reasonable to assume that if let's just say you were moving with an initial speed of VE, escape speed, as you go all the way towards infinity, you will start to slow down until such a point that you reach 0 meter per second at infinity. That's why your KE here is going to be 0. You will slow down. Okay, that's why I can say that your KE here is going to be 0. All right. So when you go towards the infinity direction, you will lose kinetic energy because you slow down. That's what I mentioned. At the same time, you will gain gravitational potential energy because there's an increase in height from the surface of the planet. Okay. So now if you try to apply conservation of energy now, let me just write some stuff here. This one is you slowing down. Therefore, KE drop. This one is you increasing height. Therefore, GPE increase. If you apply conservation of energy over here, you get the gain in GPE equals to loss in KE. Okay. So in my case, my gain in GPE will be 0 minus negative GMM over R, giving me GMM over R instead. Okay, 0 is the higher value compared to negative GMM over R because 0 is 0. Negative GMM over R is a negative value. Okay, so I take the higher value minus the lower value. So I will get GMM over R. And then after that, when I talk about the change in KE, it's just half MVE squared minus 0, giving me half MVE squared. So just now I told you that the change in KE is equals to the change in GPE. The loss in KE is equals to the gain in my GPE. I sub those equations in, I sub what I just found, I will be able to get half MVE squared equals to GMM over R, where eventually VE is actually square root 2 GM over R. Okay, so this is actually the escape speed. All right, so I think I'm going to write it out for you. Change in GPE is change in KE in one shot. So this one is 0 minus negative GMM over R equals to half MVE squared minus 0. So this one will give me GMM over R half MVE squared. So VE is negative square root 2 GM over R. Okay, so this is your escape speed. Now, your escape speed has a very similar form to something else that you just learned in this chapter. If you look at the next page, under the satellite orbits case, you notice that you also have another equation, which also relates to speed, where we say that v is square root g over, it's square root gm over r. Okay, so this one is square root gm over r. The one that you're seeing is square root 2 gm over r. The form seems to be similar. The only difference is that there's a 2. But those two are talking about two different things entirely, okay? Your square root of 2 gm over r is talking about escape speed. What's the speed that your object would need in order to escape all the way to infinity? The other one you see in the next page, square root gm over r, is talking about linear speed for a satellite or object that's moving in circular orbit around another planet. Okay, so there's a difference between those two. Well, although I'm talking about speed, they're actually talking about a different kind. One is linear speed, one is escape speed. Okay, so they're actually two different things altogether. All right. Now, the rest of the notes here is actually just telling you that your equation VE square root 2 GM over R can be changed to another different expression where it's square root 2 GR. Okay. This one you make use of the equation G is GM over R square. So if VE is square root 2 GM over R, you multiply with R over R, you're going to get 2 GM over R squared times R, where this one itself is G. So that's why you get this. But I will say this one is actually not so important, okay? Because I've never seen in your past year where they ask you to use this equation or where they ask you to express it in this equation, in this form, okay? This one I don't think is really that important. What is important is the one at the top, how you derive it, because I think because you are required to know about it a little. All right. Okay, so with this, we are actually done with gravitational field already in terms of the concept.